recording. So, last time we did a bunch of finding properties and how to fix state points and the different regions. So, as last time, what are the three regions that the fluid can be in? Type them into the old chat or say it in the Discord. I don't really care which. So it looks like Tanner and Michael are going. So we have subcooled, saturated, superheated, supercool, superheated vapor, and saturated. Yes, those are all the answers. So those are the three regions, and they exist on. Let me pull up EpicPen. They exist in different parts of this graph, right? So the subcooled region over here, anywhere outside of this umbrella on the left-hand side, saturated in here, and superheated out here. So that was just a little bit of a recap. So now we're going to do this question to start out. So this question is something like you would probably see in one of your homework assignments. It'll look something like this as you find states. All right. So let's go ahead and take a look at this one. So how you should start these questions is obviously giving it a good read, but as you go through it, write down some things that you have. So let's start off with this first one. So I'm going to pull up this right here, and I'm going to do that. So it's like kind of taking notes, you know what I mean? Take a little note about what the question says. So it says, I'll zoom back in for you guys though, so you guys can still read it. Oh my god. I don't know where I ended up there. That's what happens when you zoom in. It goes to all the hell. Okay. So it says a closed rigid container. So closed rigid container. So what does that mean so far? So what we have here is we have a closed system, right? I think you guys would agree. It says it's a closed container. What does rigid mean? What do you guys think rigid means for us? That is correct. So volume will stay the same. So so he figured that by essentially saying that right here, closed is a closed system, but rigid container means that we're just going to assume that it cannot expand or it cannot contract. It is going to be the same. It is rigid, right? It is going to be, stiff, very stiff, not going to change. So we know the following so far. Although I really need to get the brush. Yeah, live theater. So what we have so far is the following. We have volume 1 is equal to volume 2, which is equal to 0.5 meters cubed. So that is the first thing right at the start. And it said is placed on a hot plate. All right. So right there, what does placed on a hot plate mean to you? What does it mean to you guys? What would that mean to you? There is heat in, correct. So there will be some Q in, right? Very, very easily we will have some heat into the system. I don't know if it says it in the problem yet, but I'm just going to placeholder that right there. And then it says, initially, the container holds a two-phase mixture of saturated liquid, water, and saturated vapor at pressure of 1 bar. So we have found the initial state of pressure. So right here, we have P1 is equal to 1 bar, right? But what else did that tell us? Where on this in this region over here did they tell us in this question? Where is it at? So read again. It says initially the container holds a two-phase mixture of saturated liquid water and saturated vapor. So yes, we are in here. And more specifically, however, we are here. Because, although, obviously, I don't know if they give us a quality. Oh, yeah, it does. It gives us a quality of 0.5, so if you read a little longer, which I did not, you would find that x1 is equal to 0.5, so I'll go ahead and read that. So it says, saturated liquid water vapor pressure 1 with a quality of 0.5, so that means it is half and half, right, like an Arnold Palmer. So, we have a half and half mixture here. And it says, after heating, the pressure in the container is P2, which is 1.5 bar. Okay, so let's go ahead and write P2. 1.5 bar. Might just have to do that for now. All right, so we've got that. All right, and it says, indicate the initial and final states on a TV diagram and determine all of these. So A is the temperature in Celsius, states 1 and 2. B, the mass of the vapor present at states 1 and 2. If heat continues, determine the pressure in bar when the container holds only saturated vapor. Okay. So, we have a lot of stuff to do here. But first, what we should find is, this is where I like to take these questions, so I'm going to go ahead and just expand out here. We'll back it up here. So how I like to start these questions. So right here is your known box, right? This is everything we know about the question, right? How I like to start is that I don't even like to look at like what we're trying to find. What you're trying to find is not relevant yet. What we need to find is all of the properties associated with state 1 and state 2. Okay? So, let's go ahead and do that. So let's start over here. So write out state 1. 1. So state 1. What do we know? We know pressure 1 is 1 bar, right? We know x1 is 0.5 bar, right? So do you guys think we can find everything else with these two right here? At state 1, I mean, not state 2, but state 1. What is the rule? The rule is that you need 2. Okay, so Tanner, we do have one more already, but it's sort of by technicality. So I'll explain that. But let me pull up the tables. Yeah, we actually do have it. It's just it's not really a technicality, but it's something. Here, I'll find it. Where are the tables? So here we go. So right here. So let's go to the saturated water tables. So we were given pressure of 1 bar and a quality of 0.5. So technically, and I know that's that meme, technically, but technically, because we were given 1 bar, we were also given the temperature here, right? Because we're in the saturated region. So if you're in the saturated region and you are given one of these two, which you'd have to, if you're given a quality and you're given a pressure, you already know all 3 of them because you're given a pressure and a temperature, right? So we do actually know it. It's just so you need when you're in the saturated region, you still need 2 intensive properties, but temperature and pressure aren't the only things you need. It needs to be either temperature and quality, or pressure and quality, something like that. Because once you know pressure, you know temperature, and once you know temperature, you know pressure in this region. All right, so let's go back to the old paint. So can we find everything? The answer is yes. So what we need to find here are the following. I'm going to go ahead and write it. We need U1. Let's go ahead and pick up S as well, although I don't think... Actually, we'll just do a specific volume. I don't think we'll need entropy yet. I would be very surprised if they had us pick up entropy. And I don't think we will. So let's do V1. So these are the two things that we're looking to find. And now, if you remember the question or the equation that we talked about last time that had quality in it, it was the rewrite of the original quality equation, which looks like this. So UF plus X times UG minus UF, right? And we also have the same down here. So VF plus X1 times U, not U, VG minus VF, right? So these two equations right here will result in our value, the one that we are looking for our saturated condition. So we have to find our numbers here. So I'm going to go ahead and pull up the tables, and we are going to find what those look like. So right here, let's go to 1 bar and let's slide across. So we are still at 1 bar, we're sliding across. The saturated liquid value for our problem is right here. So U sub F is 417.36. So I'm actually going to pull this to the other screen so I can write it at the same time. So 417.36 plus 0.5 times, and then the saturated vapor value right here, U sub G, is 2506. Point something, 1. Okay. So does everybody see how we picked these? Essentially, I went straight across from the pressure given in the question, and I read down until I found U sub F and U sub G, and picked these two values up. Now we have to do the exact same thing, only for specific volume. So right here, we have saturated liquid volume, down, and saturated vapor volume, down. But remember, the saturated liquid volume for the SI units is times 10 to the 3, so you have to add 2 zeros to this number in order to get the correct one. So just a fair warning. So how that one ends up is the following. It ends up where we're going to write this in really quickly. So it is 0.001042 plus 0.5 times the other volume, which is 1.694, Yeah, my writing is really bad on this one, but hopefully you guys can figure that out. So let me pull this back. So right here, yeah, I apologize. I'll use the text tool from now on. Just write this stuff in there. So right here, U1 is equal to this. V1 is equal to this. Would anybody like to use a calculator and find the actual answer, or I can do it really fast? I have it next to me. Pull out my calculator and see if it works. Because I have like one of those really nice ones, but I don't know if it doesn't always turn on. Yeah, it looks like it's not going to turn on. So I can do it on a calculator on screen. That's as good as well. Scientific. All right. So let me do this on screen. So right here we have 417.36 plus 0.5 times the quantity of 2506.1 minus 417.6, close parenthesis, and you get 1461, it appears. So 1461 kilojoules per kilogram, something like that, 0.61, but I'm just going to write 1461. Save the interest of time. Now let's do the same thing with the other ones. So let's clear it. We have 0.0010432 plus 0.5 times quantity of 1.694 minus 0.00100432. And you get that. You get the specific volume to be 0.84. I'll do one more for that one. Yeah, let's do 1.847. So, and this is in meters cubed per kilogram. Okay. So, these right here are our two numbers for state one. We have the internal energy now and the specific volume now. Okay? That makes sense. So, now that we have the first state, although I'm going to have to scroll it down a bit. Is everybody satisfied with state one, right? We have everything we need to know. We have quality, pressure, temperature, internal energy, specific volume, right? Now, I'm actually going to use the text tool. That's getting to be ridiculous. So let's do that. Text. So let's do this. So let's do state 2. And then let me turn down the size just a little bit here. All right. Maybe up one more from there. Okay. So state 2. What do we know about state 2? Okay, so same volume, correct. So we have volume 2, so total volume 2 is equal to total volume 1, right? We also have pressure 2 is equal to 1.5 bar. So right now, is there any way that we can solve this? So you might think, oh, well, yeah, we have two intensive properties, right? Well, the problem is, could you with that knowledge tell me if our thing is superheated or saturated or subcooled? Remember, volume, total volume is not on that table, right? So with what we have now, can't do it, right? We need more information. So really quickly, you guys, this right here, this V2 is equal to V1. Let me draw something for you. I need to click out next time. I always do this. I was going to draw it for you, but I won't. Never mind. State 2. P2, 1.5, V1 equals V2. Okay. So, now that I've done that, let's go back to the text. So right here, you guys can see, this is our container, right? Closed, rigid. The key is here is closed. And rigid as well. They both have something to do with it. So really quick, specific volume is what? What is specific volume? Like, what are the units of it? It is volume per mass. So it is meters cubed per kilogram, right? So those are our units. Meters cubed per kilogram, right? For specific volume. So if our volume stay the same, so let's do this. So essentially it's volume per mass. And if our volume stayed the same, so remember V1 over M, V1 over M is our specific volume for state 1. And our specific volume for state 2 will be V2 over M. What about this do you guys see? What is it, what's going on here essentially? Why did I write this? Why did I write that? So you're saying that volume 1 and volume 2 would have to be the same, which is true. And also, because this is a closed container, no mass has left. Which means what? That mass 1 and mass 2 must be the same, which means that specific volume 1 and specific volume 2 is this, they're the same number, right? So V1 is equal to little v2, right? Does everybody see how that worked out before I move on? So essentially, because it is a rigid container, the volume doesn't change. Because it's a closed system, the mass didn't change. So therefore, the specific volume has to be the same from one stage to another in this type of system. All right, so I'm going to go ahead and erase this. And now that we figured that one out, let's move on. So let's move on to this. So I'm going to go ahead and write something else as a known, right? So let's go through here. Little v1 is equal to v2, which is equal to our number of 0.847 meters cubed per kilogram. Okay? And let me move this down really quick. That's not what I wanted to do. Classic. Never mind. So right here is good. So now that we know this, do you guys think that we can figure this out now? Because remember here, we now have something on the table. So we have a specific volume. We have a pressure, right? So we can at least tell where it's located, right? We don't know if it's in the middle. We can tell if it's in the middle region, saturated, or if it's saturated, subcooled, or superheated using these values. We can tell where it is, but if it's in the saturated region, we obviously need one more, right? So let's go ahead and go look at the tables. So remember our numbers. So it goes up to 1.5 bar, right? That's what we said. So the second pressure is 1.5 bar after heating. So we were given a little v value of 0.8 something. Where was that? 0.847. So 0.847. Let's go to 1.5 bar, which is right here, and go across. Is our value for our specific volume greater than this number? Or is it less than this number? Anyone? It's less than this number over here, right? So essentially, the equality, I'll write it again. So essentially, we are still in the saturated region, but instead of being 50% vapor to total mass, we are now 85%. So by heating it until the pressure reached 1.5 bar, until we added on a half of pressure essentially from where we started, we have now made it to be 85% vapor, which is good. We're slowly creeping up on superheated. But what that means is now is that we have to find equality, right? So let's head back to the old drawing board here. So let's do paint, but I'm going to use the text tool this time. So over here will be the solution. So remember, the solution, x2, this is a rewrite of that first equation. x2 will be equal to little v1, or little v2, they're the same number, but little v2 minus vf divided by, and I'm going to just enter down for a dividing sign, vg minus vf. So this right here is our equation again. V2 minus vf, and this is the vf at the new pressure. It is not at the old pressure. So this is vf and vg at 1.5 bar. So I'm going to go back to the table, and we're going to find that. So 1.5 bars VG value is 1.159. Okay, so I'm going to go bring this to the other thing, and I'll just write this as we're doing it, and I'll make sure that goes well. So text tool, bring it over. All right, so we have x2 is equal to our volume, which is 0.849 minus our VF value, which is 0.0010528, which I got from right here, 0.0010528. Then we enter down, and we go down to the next one, which is 1.159 minus 0.0010528. Okay? And I'll bring this back over. So right there, you can see our work. These are our numbers inserted from this equation to this, basically just inserted in, right? So we have 8.849 times this, or minus this, 1.159, do that. And we took it from the table at the pressure we are at, which is 1.5 bar. All right? And now, obviously, we can get an answer out of this, right? So I'm going to go ahead and do equals. Oh, that's right. I need to charge this calculator. Well, time to throw it into the old box. Never see it again. Calculator's up. So, clear it. We have 0.849 minus 0.0010532 or 28. All right, divided by 1.159 minus 0.0010528. And it looks like our quality, what was I going to say? Our quality is, oh, wait a minute. I just misspoke earlier. I just now realized what I said. 0.85 or 849 was not the quality. It's a specific volume that is now higher up representative to the other volume, to the max volume. I can now remember what I said. This is the actual quality here. Sorry about that. Yeah, I was like misspoke. So 0.7322. So just to be sure everyone's aware, what I said earlier is that when I looked at this right here, our volume was the same as state 1. Oh, well, I have 0.847. Whatever. It doesn't truly matter all that much as long as we're fairly close. But 0.847 or 849 is now a larger portion of the range of values accepted here. That's what I sort of meant to say, and I misspoke. So if you compare our specific volume to this number, and then the original number, which is this number right here, 0.1694, our volume is now closer to the end, right? It is now closer to the max value. It is closer to this number than it was in the first state, the second state at least. It's now closer. So it's making up a larger percentage of our value, of our range, than it was before. So essentially we have moved now. We have moved closer to the end goal of being superheated. So that is our value, right? So now that we have that, we can then fill out our next ones, which would be to find U1, right, is equal to UF, or this is U2, sorry. U2 is equal to UF plus X2, make sure we know that, UG minus UF. U2 is now equal to, and I will just fill in the number here. So you can watch me put this one in, but we now have UF, but we're on a new chart now, new line, which is 466.94. So I'm going to go ahead and do that. So 466.94, and I'm going to write it in here as well. So 466.94 minus our new X value, which is 0.7322, times our UG value, which I recall by looking at the table it was 2516, I believe, which I'll make sure again. 2519. 2519 minus our value that I just put in there, which is 466.94. So we'll slide over just a bit here. And it equals, whenever we type it in, some number, we'll see. So 466.94 minus 0.7322 times 2519 minus 466.94. Wait, what did I do there? 466.94. Okay, so what did I do that messed that up? Somebody with a better calculator, let me know. Why is that turning negative? Anybody? Is there something in here I'm doing wrong? Oh, I know what it is. It's supposed to be plus x2. You're right. I started looking at it now. So that number is exactly... It's just... That number is just positive. I just flipped the sign. Right? Essentially. Okay. So 1035. 35, which actually, no, that's not right. I have to redo that. I just looked at it again. You're right. 466.94. I didn't just flip the sign. It's different than that. Yeah. No, and right there, so in my first instinct, I was like, huh. Yeah, I just flipped the sign, right? But when I look at that number, so this is how I checked it. Yeah, so you are absolutely correct. So 1969 is the right answer, kilojoules per kilogram. That's basically what I got. And so really quickly, I did a mental check right after I saw that. So I said to myself, I said, if I just flip the number, it's probably the right one, right? But then I looked really fast and found out that I was wrong in an instant. And the reason why I looked at it, I was wrong, is that state 1 was before we started putting heat into the system. And this was the internal energy, right? If I would have just flipped the sign on the previous one, I would have gotten less energy while putting more energy into the system in state 2. It was less than this number, which, if you think about it for a second, how can I pour in a bunch of heat and get less internal energy inside? So that is how I immediately knew, okay, you have to redo it because I can't just flip the sign because it didn't work like that. So immediately that was my check, is that it had to make sense and it didn't. So this is something that I want to instill into you, is that it has to make sense, and what I was saying did not. And so I checked it and then I found I was wrong. All right, let's get rid of that. So 1969. So right now what we have is, we now have all of the information that we need. We have volume, specific volume 2. We have internal energy 2. We have volume 1, internal energy 1. We have all of this stuff. We have now solved everything we could possibly find, right? Now what we have to do is we have to find something else. We have to find our actual answers, right? So let's go to our actual answers. So let's see if we end up getting some of our same answers. So this right here is our specific volume of 1. We got that correct. Oh. Okay, yeah, I was just seeing to see if we got everything correct. I kind of wanted to know. Yep, 0.73, that is correct. All right. So let's go up here, right? So what it said to find was the temperature in Celsius at states 1 and 2. So let's go back here and make our answers window. So temperature in Celsius at states 1 and 2. So let's do question part A. Ugh, I really need to use the text tool. Part A. And I'll increase the font size. So part A. So part A, it says that we needed to find the temperatures at state 1 and 2. So T1 and T2. So does anybody want to take a shot at what this is? We went over this last time, by the way. This was the trick at the very end of the class. So what is the temperature at state 1 and state 2? So at state 1, we were a saturated mix, right? At 1 bar. Well, they will not be the same. Remember, because we moved up a pressure in between states. We went from 1 bar to 1.5. But they will be found in the same location. and the same location being right here. So essentially our state 1 corresponds to this temperature value, our state 2 corresponds to this one, and these two are our temperature values. So state 1 is 99.63 is our temperature, and our state 2 temperature is 111.4. So I can go ahead and write that back here. So T1 is equal to 99.6 degrees Celsius, and T2 was, what did it say, 111, I think, 0.4. So those are our first ones. Part A is done, right? We have found that. Fairly simple. Now let's do part B. Part B. So part B was to find the mass, if I recall. Let me be sure if that's what it asked. So it says the mass of the vapor present at states 1 and 2 in kilograms. Okay? So, how would everybody have an idea on how we would do this? So it is right, part B starts here. So, anybody have an idea though? Ugh, did it again. Let me find that equation. Anybody in here thinking about how we do that next part? So what do we know that represents masses, right? Like, what do we have? Anybody that like kind of can help us? We have the specific volume, that is correct. And we know that the mass of state 1 is the mass of state 2, right? So we only need to find one of them. That is also correct, right? So it says, to find the mass of the water vapor present, we first use the volume and the specific volume to find the total mass, okay? So let's scroll down here. So right here, they rearrange the equation. If you guys recall, density or specific volume, right? Oh man, that's huge. I don't know why that happened, but right here, little v is equal to big V over m, right? So they rearrange the equation and solve for mass, right? So you could end up with big V over little v, and the units cancel out to give you kilograms, right? Does that make sense? So the specific volume was the correct answer. That was the correct way to move. And then, now, here's the next part though. Because we found the mass, right? This is the mass of water vapor present. We have to find so this right here is the total mass, by the way. So total mass is 0.59 kilograms, right? This is because remember, essentially mass, this right here is this is the total mass of at state 1, before any heating has taken place or anything. This is what our mass is. So we have 0.59 kilograms inside of the bucket, inside of the container. Okay? Now, the question asks to find the mass of the water vapor. So this would be the vapor, right? And so, at state 1, so let me head back here. So let me go ahead and write this one. So mass, I'm going to do total mass is capital M. I hope you guys don't mind. So total mass is capital M. I'm going to do V divided by little v. So you can do V1s here. And that answer is equal to 0.59, right? I think that's what they ended up with. I was trying to speed things along. 0.59 kilograms. So that is total mass, right? Now, no, get over here. Okay, so now we need to find the mass of the vapor. So M vapor, in vape. Let's do that. So M vape. So how would we do this one? So if you recall, what is the quality? The quality is the mass of the vapor with respect to total mass, right? If you recall, X is equal to M vape divided by M total, right? So if you multiply our quality into our total mass, what will you end up with? The mass of the vapor, correct. So if you do x1 times m total, you will end up with 50% of it, which, I don't know, 50% of this. So 25 has 20, what, 4.5? Or not 24, what am I saying? 29.5, right? So 29.5, is that correct? Anyone want to fact check me there? So 29.5, so 0.295, right? Kilograms of vapor, right? Gets you our mass of the vapor. At state 1, though, so this is state 1, right? But obviously, it's going to be higher at state 2 because we have more vapor. So this is state 1. Then if you do it again, you do m vape 2 is equal to x2 times m total. You now have 0.59 times our 733, which was our other quality, which I don't have the mental capacity to do that one, so we'll just actually calculate that one. So 0.7322 times 0.59. So that right there gets us to 0.43 kilograms, I think is what it said. 0.432, I guess you could say. So those are our answers, right? So essentially we have found the mass of the vapor at state 1 and state 2 using the quality, right? This total mass doesn't change, but the percentage of our mass of the vapor changes, right? Because 295, this is 50% of this, right? So 295 is 50% of this. This is 73.2% of this, because obviously we heated it up, right? And then we got more vapor as we heated it up, okay? All right, so now the last bit is to make a chart of this. It's a chart of this right over here. So I'm going to go ahead and draw a little, I'm going to try and draw a really nice one. Yep. And we can move up just a little bit on here. So we have this, right? And I'll freehand the rest of it. So this right here, we'll just call this, I think they asked for a PV diagram. I don't recall which one they asked for. We'll see. It says they wanted on a TV diagram. Okay, cool. So, TV diagram. So really quickly, we have 3 lines, or we have 2 lines of pressure in this problem, right? So temperature, remember, when we hit this region, stays constant, okay? So let's call our first temperature to be right here, which I'm actually going to use the line tool again. Our first temperature line is going to be right there. First temperature line is there, which is our T-sat of our first one, which is, let me draw that across as well, our temperature to be 99.6, right? That was our first temperature. And now we move up here to our second temperature. Our second temperature was the following. It was 111. I'm just going to write 111 because I don't remember what the point was. Although it's down beneath me somewhere, isn't it? No, it's not. Oh, it is 111.4. So right there are our 2 temperatures, right? And let me go ahead and I exaggerated them. Those on this chart, they'd actually be like a lot closer together. I just wanted to show like the exaggeration, right, between them. So this right here is what we're at. And now I have to finish the rest of it because the rest of it has to show pressures. And how lines of constant pressure go in this class are like this. So these lines right here represent pressures. And obviously there are infinitely many of them on this chart. Like they're just like really, really close together all the way until you fill in you fill in the whole thing, right? But I just showed you an exaggerated line. And so this is how the one should look. So right here, this is 1.0 bar. That line of constant pressure is 1 bar. This one right here is 1.5 bars, right? And so we have a temperature line that stays the same here. And on this line is constant pressure. So we are not changing pressure while on this line. So now let's go ahead and draw the process in a sense, right? So the first process was heating, right? Or the only process. But we started here at state 1. I'm just going to draw us a little line right here. Fill. Let's do that. So that right there is state 1. So I'm going to go ahead and draw that. So that's state 1. State 1 ended up right there. We are about 50% through the thing, right? Because remember, our quality is 50 for state 1. About 50% through. Now, what ends up happening is that we go straight up, essentially, right? Would you guys agree? Essentially, we go onto another pressure line. We get a bunch of energy and end up going up, right? So I'm going to put that somewhere here. Although it looks a lot better when you end up drawing it, or whenever they have it on like the perfect chart. But on mine, it's going to look a little bit off-centered. But right here, we have state 2, right? So state 2, all we did was we heated it. So we increased the temperature, and we also increased the pressure, right? Because as we increased the pressure, the temperature increased, and we went up, 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 until we got to 1.5 bar. And because of that, because our specific volume stayed the same, although this is the reason why that, oh, this is a TV diagram, I remember. Now I remember why it's straight up and down. So, TV. Sorry about that. So because it's a TV diagram, we have to show you that volume stayed the same from state 1 to state 2. That is why it's right up and down. I always am thinking of TS because TS diagrams are the ones that you'll see the most of. So that's why I was thinking it didn't change, it had to stay up and down, but it does because this is a TV diagram. Because if you guys know, in between states 1 and 2, the volume did not change. Specific volume did not change. So right here is what our process looked like. This right here is what you would call constant volume heating. So constant volume heating to this pressure. Okay? So this was a constant volume heating process from this line to this line. Volume stayed the same, temperature change and pressure change to get us here. Okay? So does everyone see how this one looks? And I can go back and see theirs because theirs is probably better. I think I just saw it anyway. I think it's this right here. So I only drew this part of it because the last part we don't have time for. It asks about where would it end up if we continued heating it until saturated vapor, right? That's what their next thing is. But this is the part that I wanted to show you, is this. This is what it should end up looking like. Constant volume heating. And really quickly, if you were to do that next part, it would be the exact same. Essentially, also if the heating continues, determine the pressure when the container holds only saturated vapor. So what that would mean is that you would set your V value. You would go V3 is equal to VG, right? Essentially, it is now saturated vapor. Your volume is now saturated vapor. So what you would do is you would go down the table. So I'll explain this really fast, I guess. So you would go down the table here and find 0.849, which I think is our original and only saturated, or our only, 0.847. So what you would do is you would go down the table really fast and you would find a saturated vapor value that equals that number. Okay? So let's go do that just to show you really quickly. So this one right here requires no more computation. It only requires you to know the tables. And so what you would do is you'd go to the saturated vapor column and you would go down until you find 0.849, right, or 8.7. So you guys would realize it is somewhere in between 2.5 and 2, right? So what you'd have to do is you'd have to interpolate between these two numbers, knowing you would know a third specific volume, and you have to do it between pressure. So you would do x1 is this, x2 is this, y1 is 2, y2 is 2.5, and you would get y3, or I think it's actually, no, it was the other way. I think it's this is x1, this is x2, x3 would be the pressure in between that we don't know. Y1 is this, y2 is the other one, and then you insert your specific volume in here, and you would end up interpolating using that formula, and you would find that our value is, I'm going to guess like 2.1 or something. I don't know what they say. 2.11. Look at that. So 2.11. And by the way, the reason why I was able to guess that, not because I actually saw the answer previously, was because if you look at this right here, if you look at this number, 0.849, right, which is where we were at, is a lot closer to this number than it is to this number, right? Would you guys agree? It's way closer to this one. So I just took it as it's got to be closer to this one, and so I just did 2.1. So that's how I figured it out. Does that make sense? Hopefully, how that last part was done. Okay, so I'm going to go ahead and stop this then.